This is the presentation for a paper, Communication Efficient Decentralized Track Fusion using Selective Information Extraction. The paper is presented by me, Forsling. I am an industrial PhD student from Saab, doing my research at Linköping University in Sweden. The paper is written together with Zoran, Sjanic, Fredrik, Gustafsson, and Gustaf Hendeby, and is included in Block A, Track 1, Advances in Distributed Kalman Filtering and Fusion, number 1. This paper considers a decentralized sensor network where the cross-correlations between the estimates are unknown. Further, we focus on consistent estimators and communication efficiency, where only the useful information is being exchanged. When speaking of information in this scope, we refer to the inverse of the error covariance. An estimate is given by the pair x hat and p, where x hat is the state estimate and p is the covariance matrix reported by the estimator. When necessary, we will also use subscripted indices for estimates. Our problem can be illustrated by the figure to the right. Two estimates are provided for an unknown true state x. The first estimate is given by the yellow ellipse, and the second estimate is given by the red ellipse. Say now that estimate 1 is to be fused with information extracted from estimate 2 along only one direction. In this case, it is obvious that the information from estimate 2 along the z direction should be used. Since it is in this direction, estimate 1 lacks information. This was a rather simple problem. The question is then, what happens in more complex scenarios with high-dimensional states and arbitrary information ellipsoids? Is it always the most informative directions that should be exchanged? As you will see, it is not always the case. The approach to the stated problem is to formulate methods that are able to distinguish what information is useful in the network. In other words, we seek methods that selectively extract local information that is globally useful. Since information is being passed around, unknown cross-correlations arise as a natural part of decentralized sensor networks. In the joint covariance matrix to the right, the cross-correlations are represented by the off-diagonal matrices. Simply neglecting the cross-correlations is not a particularly good idea, as this would imply informations will be double counted. One common approach to handle unknown cross-correlations is to construct conservative estimates, meaning that the actual covariance is bounded from above by another covariance. This leads us to the notion of consistency. An estimate x hat and p of a true state x is consistent if p is larger than or equal to, in the positive definite sense, the actual covariance. The actual covariance is given by this expectation value, where x tilde is the true error. A consistent estimate is also called a conservative estimate. A conservative estimator is reliable and robust, but does not come for free. Since information is inversely proportional to the covariance, inflating the covariance by replacing it with a conservative bound means that information will be lost. That is, there will be a gap between the actual covariance and the calculated covariance p, a gap directly related to the information loss. A geometrical interpretation is provided by illustration. The larger the gray area between p and the actual covariance, the larger is also the information loss. Extracting information will depend on the specific fusion architecture. In a centralized sensor network, the fusion center has direct access to the observations from the sensors. The common and reasonable assumption is that the observations are mutually uncorrelated. This means that it's rather straightforward to utilize all information extracted by the sensors. In a decentralized sensor network, the underlying sources responsible for information extraction are still the sensors. However, in this case, except for any local sensoring device, the fusion centers have access to estimates instead. And this makes the information extraction sources hidden to the fusion centers. Hence, the information extraction must be done on the estimates, which might be correlated to some unknown degree. Since we want to ensure consistent estimates, in this work, not all information extracted by the sensors can be utilized. Still, we want to maximize the amount of information being extracted. In the next Three methods for selecting information projections are proposed, where an information projection is a projection of the information ellipsoid along one direction. The information selection is done in each fusion node prior to exchanging information. The information selection requires no other information than the information that has been exchanged within the network. The parameter ns defines the number of information projections used. In the largest eigenvalue method, the information selection is exclusively based upon the information matrix P inverse. This matrix is factorized using the eigendecomposition. Then simply the ns most informative eigenvalues and the corresponding eigenvectors are picked. The state estimate is also projected along the ns chosen projections. One possible issue with this method is that once the most informative eigenvalues have been exchanged, they will repeatedly be selected for transmission, such that only these projections travels around in the network. A more sophisticated method is the transmitted information method illustrated on this slide. Here another covariance P bar is introduced to represent the summary of the previously transmitted information. P bar is kept locally in each fusion center. All information being transmitted from a fusion center is also fused with P bar in the TI filter. The main filter fuses estimates received by the data link and measurements with the current track estimate. The information is done as follows. The set IS holds NS orthogonal information projections picked from P inverse. F resembles the span of all possible sets IS. Each entry of F is then fused with P bar inverse. The information selection is then given by the IS that improves P bar the most. As old information should be forgotten, process noise is added to P bar at each time update. The received information method is similar to the transmitted information method. The only difference lies in how the reference covariance P bar is calculated. In this case, P bar is calculated by fusing only information previously received by the data link. As in the transmitted information case, information is selected such that P bar is improved as much as possible. To investigate the performance of the three proposed methods, a simulation study has been made. Two scenarios are studied, where the blue nodes each contain a sensor and a fusion center and are also able to exchange filtered estimates. The red node is the target of interest. The sensors have good bearing accuracy but poor range accuracy. In scenario 1, geometry is good from a triangulation perspective as the blue nodes are separated by a large distance. In scenario 2, geometry is poor, implying that it will become more difficult to extract information. New measurements are generated at 1 Hz, and also the estimates are exchanged at 1 Hz. To solve the optimization problem in the transmitted information method and the received information method, only projections of P inverse along the eigenvectors are considered. Information received via data link is fused using covariance intersection. The root mean squared error is used to evaluate the performance. To evaluate consistency, the normalized estimation error squared metric is used, but the result from this consistency evaluation is not shown here since all methods were found being consistent. CRLB is the Kramer-Rao lower bound. CKF is a centralized Kalman filter having access to all measurements. LKF is a local Kalman filter with only access to local measurements. CIP is a covariance intersection where the full information P inverse is exchanged. In scenario 1, we can see that initially it is beneficial to select the largest information eigenvalues, but after a few seconds, these do not allow for any new information to be extracted. The bumps at around 10 seconds for the largest eigenvalues method curves indicate that the largest information eigenvalues are not always the best to exchange from a fusion perspective. Received information in this case needs ns larger than 1 to yield any gain. Transmitted information provides good performance already at the ns equal to 1. The larger the ns gets, the better the performance gets. In scenario 2, it is generally much more difficult to extract information. The largest eigenvalue method does not yield any fusion gain at all. since in this configuration it is not the largest information eigenvalues at one node that are complementary information for the remaining nodes. Both the transmitted information and the received information methods are able to extract information in case of n is larger than 1. In this paper, the problem of decentralized estimation with efficient communication has been studied. To cope for the requirement of efficient communication, the concept of selecting and fusing projected information has been introduced. 3 methods, the largest eigenvalue method, the transmitted information method, and the received information method, have been proposed to handle the problem. The take-home message is the following. At first, using only the estimates exchanged on the data link, it is possible to select which information is useful in the cooperating network. Secondly, maximizing the fusion gain is not necessarily achieved using the most informative projections. So, thanks for listening. Please read the paper and I hope I see you on the Q&A.